Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
This is Andrew and Renee. Welcome to the Stack series.
Today we are exploring carbon capture, utilization, and storage, often called CCUS.
And, this is one of those topics that feels like it's absolutely everywhere and, well, nowhere at the same time.
Right.
You see the headlines constantly. You see all these corporate promises of net zero by 2050.
Absolutely.
But when you actually start to peel back the layers, and we have a huge stack of research in front of us today, you find yourself in the middle of one of the most polarized, complex, and honestly chemically fascinating subjects in the entire climate toolkit.
It really is. I think for a long time, I just had this mental image of a giant vacuum cleaner. You just point it at the sky and, suck up the bad stuff. It seems so straightforward.
We all had that image, I think.
But as we went through these sources, it became very clear, very fast, that this isn't just about sucking carbon out of the air. Not at all. This is a massive industrial chemical engineering challenge. I mean, we are talking about rewriting the way we process gases on a planetary scale.
Precisely. And the stakes, well, they couldn't be higher. We're looking at a technology that the IPCC, that's the Intergovernmental Panel on Climate Change, and the International Energy Agency have flagged as, frankly, crucial.
They've basically said it's non-negotiable.
They've essentially said, look, we can't hit our climate goals without this. And yet, as we are going to see today, this technology faces hurdles that are fundamental. We are battling physics, we are battling economics, and we are battling some very, very thorny ethical questions.
So our mission for this conversation is to move beyond the press releases, beyond the headlines. We want to really understand the chemistry of how you actually catch a gas molecule that really doesn't want to be caught.
And then the geology of where on Earth do we put it all once we've caught it?
Exactly. And finally, we need to look at the societal cost. Who pays for it? And just as importantly, who has to live next to it?
It's a story of molecules and morality, really.
I like that. Molecules and morality. Okay, let's get into it. We need to start with the foundations. What do we actually know for sure? And I think the first thing we have to do is draw a really clear line between the two big flavors of carbon capture, because people mix these up all the time.
All the time. Broadly, you have point source capture on one side and direct air capture, or DC, on the other.
Okay, and point source that's like catching at the scene of the crime, right? The factory smokestack, the power plant.
Exactly. And that's the key difference, because that's where the physics is slightly more forgiving. If you're at a coal plant or a cement factory, the flue gas coming out might be, say, 10% or even 15% carbon dioxide. That's a high concentration.
Can you give us an analogy for that? Because percentages can feel a bit abstract.
Sure. Think of it like looking for a red marble in a jar of blue marbles. If 15% of the marbles in that jar are red, you can reach your hand in and grab one pretty easily. You don't have to sift through millions of blue ones just to find a single red one. The target is dense.
Okay, that makes sense. Whereas direct air capture, or DAC, is trying to pull it right out of the wind.
Yes. In the ambient air we're all breathing right now, CO2 is only about, 0.04%? That's roughly 420 parts per million.
So tiny.
So tiny. Using our analogy, that's like trying to find one specific grain of red sand on a massive, massive beach of white sand. The sheer amount of energy required to process enough air to get a meaningful amount of CO2 is just exponentially higher. You have to move so much air, so much of the other stuff, just to find the carbon.
You have to run the fan a lot longer to catch the same amount of material.
A lot longer. And a much bigger fan. So for this first part of our exploration, we're really going to focus on point source capture. That's where the mature technology lives. That's the heavy industry application that's been around for a while.
Okay, so let's talk about that mature technology. When we say mature, we're talking about something that's been around for decades, right? This isn't science fiction.
Oh, no, not at all. We've actually been doing this in some form since the 1930s. It was mostly used in the natural gas industry to, clean up gas streams. The absolute standard method, the one everyone uses, is called chemical absorption. Or you might hear it called wet scrubbing.
Wet scrubbing.
And the star of the show here is a class of chemicals called aqueous amines, specifically a molecule called monoethanolamine, or MEA for short.
MEA, I remember reading about this, and the analogy that really made it click for me is chemical Velcro.
That is a perfect way to visualize it. It really is. But let's dig into why it acts like Velcro. Because it's not magic, it's just chemistry. It all comes down to the nitrogen atom in that amine molecule.
Okay, take us down to the molecular level.
So this nitrogen atom has what chemists call a lone pair of electrons. You can picture it as a little negatively charged hook that's just sticking out looking for action. It is chemically desperate to bond with something acidic.
And carbon dioxide is an acidic gas.
It's an acidic gas, so it's a match made in heaven, or, well, a match made in a smokestack. When that CO2 molecule floats by, that nitrogen hook just grabs it. They undergo a pretty fast chemical reaction and form a new, more stable compound called a carbimity. It's not just holding hands, they've actually merged into a new molecule.
Wow. So walk us through the factory floor. We have this hot, dirty flue gas coming out of a power plant. What happens next?
Okay, so step one is the absorber column. It's a massive tower. The flue gas enters at the bottom. But here's the first catch, and this is a really important one. The gas has to be cooled down first, usually to around 40 degrees Celsius, which is about 104 Fahrenheit.
Why do you have to cool it? Usually heat makes chemical reactions go faster, doesn't it?
In many cases, yes. But this specific reaction, the Velcro snapping shut, is what we call an exothermic reaction. It releases heat. And by the laws of thermodynamics, Le Chatelier's principle, if a reaction releases heat, it actually happens more efficiently at lower temperatures. If it's too hot, the bond won't form properly. The Velcro just won't stick.
Got it. So you're setting the right conditions. So we cool the gas, and then what?
Then you rain this liquid amine solution down from the top of the tower. It's literally like a chemical shower. The gas rises up from the bottom, the liquid falls down from the top, and they meet on the surface of special packing material inside the tower that maximizes the contact between them.
And the amine just snatches the CO2 out of the rising gas.
It does. The amine grabs the CO2 and all the other stuff, mostly nitrogen and a little bit of oxygen, goes straight out the top of the tower into the atmosphere as clean gas.
Okay, success. We caught the carbon. But now we have a different problem, don't we? We have a huge tank full of this rich solvent, the amine, that's now saturated with CO2. We can't just store that liquid forever. It's way too voluminous, and the amine is expensive. We need to reuse it.
Right. We need to get the CO2 off the Velcro so we can compress the pure CO2 gas for storage and send the lean amine back to the shower to catch more.
And this is where the energy bill comes due. This is the big catch.
This is the thermodynamic tax you have to pay. To break that very stable chemical bond, to rip the CO2 off the amine, we have to send the rich solvent to a second separate tower. This one is called the stripper, or the regenerator.
And what happens in the stripper?
We have to boil it. We have to heat it up significantly, usually to around 120 degrees Celsius or 250 Fahrenheit. We pump a lot of steam into it. This process is called a thermal swing. The heat provides the energy needed to reverse the reaction and break the bond.
And the problem isn't just heating the amine molecules themselves, is it? It's the water.
That's it. That is the crucial inefficiency of this whole process. These amines are dissolved in water, usually a solution that's about 70% water. And as you know, water has an incredibly high specific heat capacity.
Can you break that down for us? What is heat capacity?
Think of it as thermal inertia. It takes a huge amount of energy to change the temperature of water even by 1 degree. It's why your pot of water takes so long to boil for pasta.
Right.
So, to release the CO2, you are essentially boiling huge cauldrons of water over and over and over again in a continuous loop. You're not just heating the active ingredient, the amine, you're heating the carrier fluid that makes up most of the volume.
That sounds incredibly wasteful.
It is. This is what engineers call the parasitic load. You are using a significant chunk of the power plant's own energy output just to run the capture machine attached to it.
So let me see if I have this straight. You burn coal to make steam to turn a turbine to make electricity. But then you have to take, say, 20 or even 30% of that steam or electricity and divert it back to boil water to catch the CO2 from the coal you just burned.
That is the loop. You've got it exactly right. And that energy penalty is the Achilles heel of amine scrubbing. It's the fundamental reason why it's so expensive and why it reduces the net power output of a plant.
Now, the sources did mention an alternative to this chemical Velcro, something called physical absorption. How is that different?
So if chemical absorption is Velcro, then physical absorption it's like a soda stream.
Okay, carbonation, I can picture that. Making fizzy water.
Right. It relies on a basic law of physics called Henry's law. This law just states that the amount of a gas that can dissolve in a liquid is directly proportional to the pressure of that gas above the liquid.
So more pressure, more gas dissolves.
Exactly. You pressurize a liquid with CO2, and the gas molecules just sort of squeeze into the empty spaces in the liquid. They don't form a strong chemical bond. They're held there by weak physical forces. We call them van der Waals forces.
So it's more like the CO2 is just kind of sitting in the gaps between the liquid molecules.
It's just hanging out in the empty spaces. It's a physical solution, not a chemical reaction.
And what about getting it out? Is that part easier?
Much, much easier and much cheaper. To get the CO2 out, you don't need to boil it. You just release the pressure. It's like opening a bottle of soda. The gas comes right out of the solution. This is called a pressure swing.
That sounds way better. No heat, no massive energy bill to boil water. Why on earth aren't we using that everywhere?
Because of the pressure requirement. Henry's law only works well if the gas stream you're trying to clean is already highly pressurized and has a lot of CO2 in it to begin with. It's great for things like natural gas processing or some pre-combustion systems where the gas is already squeezed to high pressures as part of the industrial process.
But for a standard power plant smokestack,
The pressure is low. It's basically at atmospheric pressure.
Yeah.
If you tried to use physical absorption on that flue gas, almost no CO2 would dissolve. You'd have to spend a fortune on massive compressors to squeeze the entire gas stream before you even started the capture process.
which would create its own massive energy penalty.
Exactly. It would completely defeat the purpose. So for now, for most of these standard pollution sources, we're kind of stuck with the chemical Velcro.
Okay, let's fast forward a bit. So we've used the amines, we've boiled the water, we've stripped the CO2, and now we have this stream of almost pure CO2 gas. We compress it into something called a supercritical fluid, which just sounds incredibly cool, by the way.
It is cool. A supercritical fluid is a really strange state of matter. It happens when you pressurize a gas past its critical point. The CO2 becomes dense like a liquid, so you can pump it efficiently through a pipe. But it has the low viscosity of a gas, so it flows very easily with less friction. It's the most efficient way to transport it over long distances.
So we have this liquid gas ghost fluid. Now we have to put it somewhere. This is the storage part of CCUS. Where does it go?
It goes deep underground. We are looking at deep geological formations, usually a kilometer or more beneath the surface. The main candidates are saline aquifers, which are just deep, porous rock layers filled with very salty water that we can't drink or use for agriculture, or alternatively, depleted oil and gas fields.
It feels a bit like putting the genie back in the bottle, doesn't it? We took the carbon out of the ground as coal or oil, burned it, and now we're trying to shove it back underground.
That's a very good way of putting it.
But what keeps it there? I mean, it's a gas, even if it's a dense one. It's more buoyant than the water around it. Why doesn't it just bubble back up to the surface over a few years?
That is the billion-dollar question. And the answer is security. Geologists talk about 4 distinct locks or trapping mechanisms that work together over different timescales. It's really important to understand these because this is what stands between us and a massive leak.
Okay, let's go through the 4 locks. What's number 1?
The first and most immediate one is structural trapping. This is the most straightforward. It's just like how oil and natural gas are trapped naturally over millions of years. You inject the CO2 into a porous rock layer, like sandstone, but above that sandstone is a thick, impermeable layer of rock, like shale or clay. I call this a cap rock.
So it's a physical sealing, a lid on the container.
Exactly. The CO2 is buoyant, so it wants to float up. It rises through the sandstone until it hits the bottom of that shale cap rock, and it just stops. It spreads out underneath it. Simple physics.
Okay, that's lock number 1, the primary containment. What's lock number 2?
That would be residual trapping. This is a bit more subtle. Imagine you have a kitchen sponge. You soak it completely in water, and then you squeeze it out as hard as you can. It's still damp, right?
Yeah, you can never get it totally dry just by squeezing. There's always some water left.
Right, and that's because tiny little droplets of water are stuck in the microscopic pores of the sponge by something called capillary force. The exact same thing happens with CO2 underground. As the main plume of gas moves through the rock, tiny blobs of it get left behind, stuck in the microscopic pore spaces. They are physically immobilized. They can't move up or down anymore.
So it gets snagged on the rock itself, on a micro level.
Yeah.
Interesting. Okay, lock number 3.
Solubility trapping. This happens over a longer time scale. We're talking decades or centuries. The CO2 slowly dissolves into that salty brine deep underground.
Like our soda stream again.
Exactly like the soda stream. And
Okay.
here's the really cool part. Water that's saturated with CO2 is actually slightly heavier, slightly denser than regular salt water. So once the CO2 dissolves, it's no longer buoyant, it's no longer trying to float to the surface, it starts to slowly sink. This mechanism actually makes the storage more secure over time.
That's reassuring. It's a self-securing system in a way. And the final lock, the ultimate goal.
Mineral trapping. This is the holy grail of storage. The dissolved CO2 makes the water slightly acidic. It forms carbonic acid. This acidic water then reacts with the minerals in the surrounding rock, especially rocks that are rich in elements like calcium, magnesium, or iron.
And what does that reaction do?
It forms new, solid carbonate minerals. It literally turns the CO2 into stone, calcite, magnesite, siderite. Once that happens, it is never, ever coming back up. It is permanently part of the solid geology of the Earth.
That sounds incredibly secure. Just listening to that, you think, okay, problem solved. Engineering works.
Right.
But as we move into our second section, the active debate, we start to see that this neat picture has some cracks in it.
Figurative and, well, literal cracks in some cases.
Right. Let's talk about the controversy. Because for something that sounds like such a tidy engineering solution, there's a lot of disagreement in the scientific community about whether this actually works at the scale we need it to.
There is. And a lot of it starts right back with that energy penalty we talked about. We need to look at what critics call the carbon penalty.
This is the deep irony I hinted at earlier.
It is the great thermodynamic irony of carbon capture. Because that amine scrubbing process requires so much heat to regenerate the solvent, a power plant that has carbon capture equipment bolted onto it becomes significantly less efficient. It has to burn more fuel, more coal, more gas to generate the same amount of electricity for the grid.
Why more?
Because so much of the energy it's producing is being diverted to run the capture plant instead of going to the grid.
So you are generating more CO2 at the source just to run the machine that catches the CO2.
Exactly. And let's say your capture efficiency isn't 100%, and it never is. It's usually designed for 90%. If you're burning, say, 25% more fuel to capture 90% of the CO2, well, the math starts to get a little fuzzy.
And that's not even counting other emissions.
Right. If you have upstream methane leaks from mining that extra coal or drilling for that extra gas, the net life cycle reduction of carbon can be significantly lower than what's advertised on the tin.
So if a company says, we captured 90% of our smokestack emissions, that might not be the whole truth about the total impact on the atmosphere.
Correct. Some of the more critical studies argue that in worst-case scenarios, especially with leaky supply chains, you're running very fast just to stay in almost the same place. You aren't actually reducing the atmospheric load as much as the brochure says you are.
That leads us to the big reassessment of storage, the place we're going to put all this stuff. I was really struck by the source referencing the 2025 Nature study by Matthew Gidding. For years, I've heard these huge numbers thrown around like, we have enough storage space for centuries.
That has absolutely been the standard line from industry and even some government agencies. The theoretical capacity number that gets floated around is about 14 trillion tons of CO2 storage available globally.
Which is a massive number.
It's an astronomical number. It implies we have a basically unlimited resource, an infinite garbage dump for carbon.
But Giddens' team says, not so fast.
Right. They did a much more reality check. They didn't just look at the total volume of porous rock. They calculated what they call the prudent capacity. They looked at real-world logistical constraints. Can you actually build a pipeline to that location? They looked at safety margins to avoid overpressurizing the rock. And most importantly, they looked at geological reality. Is the caprock thick enough? Is the permeability right?
So after all that filtering, what was their number?
About 1.46 trillion tons.
Whoa. Wait, from 14 trillion down to 1.46? That is 10 times less.
It is a full order of magnitude drop. Now, to be clear, 1.46 trillion tons is still a lot of space. It could buy us decades of time. But it fundamentally changes the conversation. It means storage is a finite, precious resource. It is not an infinite garbage dump. It means we have to be very selective and strategic about what we choose to capture and store. We can't just assume we can capture everything forever.
And speaking of not capturing everything,
Yeah.
let's talk about the current scale of this technology. Because the hype is huge. Every major oil and gas company has a net zero plan that relies heavily on this. But what is the reality on the ground today?
It is microscopic. It's almost negligible if you exclude its use for enhanced oil recovery, which is a separate controversial issue we'll get to in a minute. The amount of CO2 currently captured and permanently stored is about 10 million tons a year, globally.
And to put that number in perspective for us,
Yeah.
how much do we emit as a planet every year from fossil fuels?
We emit roughly 37 billion tons a year.
So 10 million out of 37 billion is
It's 0.03%.
0.03%.
It is a rounding error, and critics look at that number and they say, this isn't a climate mitigation tool right now. This is a rhetorical device. It allows companies and governments to say, we're working on it, and to delay meaningful regulation, even though the technology isn't deploying at anywhere near the speed required to make a dent in the problem.
Okay, let's talk about the safety risks. We mentioned putting this gas underground. But the Earth isn't a static, inert container. It moves. It has stresses.
It does, and one of the biggest risks geologists worry about is induced seismicity.
Man-made earthquakes.
Yes. When you inject fluids, any fluid, whether it's water or CO2 under high pressure deep underground, you increase what's called the pore pressure in the rock. This can act like a lubricant. If there's a dormant, pre-existing fault line nearby that is already under tectonic stress, that lubrication can be the final straw that causes it to slip.
We've seen this happen with fracking wastewater disposal, right, in places like Oklahoma and Texas.
It's exactly the same physical mechanism. Injecting fluid greases the fault. So site selection becomes absolutely critical. You cannot just pump this stuff anywhere. You have to do extensive geological surveys to avoid known faults.
And then there's the more direct risk of leakage. We talked about those 4 locks, but locks can be picked or they can fail. And the weakest link in any geological storage site is usually the man-made part, the boreholes.
The wells, especially the old wells that were drilled to get the oil and gas out in the first place. You have to remember, a mature oil field might be like a pincushion. It could be riddled with hundreds of old wells, some of them plugged with cement from the 1950s or 70s, using standards that are not what we'd use today.
And cement doesn't last forever, I'm guessing.
Especially not in this particular chemical environment. Remember, when CO2 mixes with that underground salt water, it forms carbonic acid. It's a weak acid, but it's persistent. And that acid is corrosive. Over decades, it can eat through old cement plugs and steel well casings.
And if those old wells fail, they basically become chimneys.
They become highways for the gas to escape right back to the surface.
And if it does escape in a large quantity, it's not just that it goes back into the atmosphere and warms the planet. There's an immediate, acute danger to people and animals nearby, right? Because CO2 isn't like smoke. It doesn't just float up and away.
No, absolutely not. CO2 is about 1.5 times heavier than air. If a pipeline ruptures or a reservoir has a massive leak, the gas sinks. It hugs the ground. It flows downhill into valleys and low-lying areas, displacing the oxygen as it goes.
This is the asphyxiation risk.
It is. There's a terrifying natural precedent for this called limnic eruption. It happened at Lake Nyos in Cameroon back in the 1980s. A huge bubble of naturally occurring CO2 came out of the deep lake, flowed down the surrounding valleys for miles, and suffocated over 1,700 people and thousands of livestock, many of them in their sleep.
That is a genuine nightmare scenario.
Now, an industrial leak might not be on that massive geological scale, but the physics is identical. If you are in a valley that fills up with invisible, odorless CO2, your car engine will stop working because there's no oxygen for combustion, and then very quickly you stop breathing. Pipeline safety and storage integrity have to be taken incredibly seriously.
That is a terrifying thought. And it brings us to another pollution issue that I, for one, hadn't even considered before digging into this. The amines themselves. We talked about the solvent degrading.
This is sort of the dirty secret of the chemical absorption process. That amine solvent doesn't last forever. The harsh conditions inside the machinery, the heat, the oxygen, cause it to break down over time, and some of it vaporizes and goes out the smokestack along with the clean gas.
And what happens when those amine compounds get into the atmosphere?
They don't just disappear. They react with sunlight and other pollutants like nitrogen oxides to form a whole new class chemicals, primarily nitramines and nitrosamines.
And those are bad.
Those are very bad. Many of them are known or suspected carcinogens. They can also be toxic to aquatic life when they fall back to Earth in rain. So we have to be extremely careful that in solving one massive environmental problem, CO2, we aren't accidentally creating a new, localized toxic rain problem for the community living downwind of the plant.
There's one more hugely controversial topic in this section we absolutely have to touch on. It came up in almost every single source. Enhanced oil recovery, or EOR.
This is the elephant in the room of the entire CCUS industry. Right now, the main economic driver for most of the carbon capture that's happening in the world isn't saving the planet. It is extracting more oil.
Can you explain how that works? Why do oil companies want to buy CO2?
Well, in an aging oil field, after you've pumped out all the easy stuff, there's still a lot of oil left, but it's thick and stuck to the rock. So oil companies will buy CO2, pump it down into these old fields.
And what does it do down there?
Two things. First, the CO2 acts as a solvent. It mixes with the residual oil underground and lowers its viscosity. It makes it thinner, more slippery. Second, it repressurizes the whole reservoir. This combination pushes stubborn, hard-to-reach oil out of the ground that you otherwise couldn't get to.
So we are capturing carbon to produce more carbon.
That is the heart of the debate. The industry argues that EOR provides the crucial early revenue needed to build the expensive pipeline infrastructure for a future climate-focused CCUS industry. They say, look, a lot of the CO2 stays underground permanently, so it's a net positive.
But is it? What do the critics say?
Critics and many environmental groups look at things like the 45Q tax credit in the United States, which basically pays companies to do this, and they argue it is just a massive subsidy for the fossil fuel industry. It extends the life of old oil wells that should be shutting down. If the carbon you capture is then used to pump up oil that, when burned, emits more carbon into the atmosphere, have you actually accomplished anything for the climate? It's a huge question.
It's a very complex, tangled web. It seems like every solution has a shadow side. But I want to pivot now. We've looked at the foundations, we've looked at the serious problems and debates, but science doesn't stand still. Let's look at the frontiers. What might change everything?
This is where it gets really exciting. This is where you see the incredible ingenuity of chemists and material scientists coming into play. And we have to start by talking about the 2025 Nobel Prize in Chemistry.
Yes, this was a huge deal. It was awarded for the discovery and development of metal organic frameworks, or MOFs.
MOFs, a field pioneered by scientists like Omar Yaghi. And the best way to think of these materials is as molecular tinker toys, or maybe molecular sponges.
Okay, I played with tinker toys. You have the wooden sticks and the round connector hubs.
It's exactly that, but at the atomic scale. In a MOF, you have metal nodes, those are the hubs, and you have organic molecules that act as linkers. Those are the sticks. And by carefully choosing which sticks and which hubs to use, chemists can build these incredibly ordered, crystalline structures with very specific shapes and, crucially, very specific pore sizes. You can design them atom by atom.
And they are porous, right? That's the key.
They are unbelievably porous. The internal surface area is just mind-boggling. If you were to take a single gram of a common MOF material, a chunk the size of a sugar cube, and you could magically unfold all of its internal surfaces.
How big are we talking? A tennis court?
Several football fields.
You're kidding me? A sugar cube with the internal surface area of several football fields.
It's the magic of nanogeometry. And what that means is that there are millions and millions of potential places for gas molecules to stick. And because you can tune the pore size with incredible precision, you can make a MOF that fits a CO2 molecule perfectly, like a key in a lock, but is the wrong shape for the slightly smaller nitrogen or oxygen molecules to fit into. It becomes highly selective.
So going back to our earlier discussion about amines, is this better than the chemical Velcro?
Potentially, yes, much better. Certain families of these materials, like the MOF74 family, show incredible capacity for adsorbing CO2. But the real kicker is the regeneration. Because the CO2 is often just physically trapped in these cages or very weakly bound, you don't need to boil tons of water to get it out. You can often release it with a much smaller temperature change or even just a change in pressure.
So the energy penalty, the parasitic load, it just drops.
It could drop drastically. And if you can do that, you change the entire economic equation of carbon capture.
That could be a true game changer. But there's another frontier that moves away from heat entirely. The sources talked about electrochemical capture.
The electric switch. This is a fascinating area of research because it integrates perfectly with a renewable energy grid. Instead of using a thermal swing, which requires heat and steam, you use a voltage swing or a pH swing driven by electricity.
How does the pH swing work?
Well, we know CO2 is an acidic gas. So the idea is you use electricity, say, from a solar panel to split water molecules and make a solution basic or alkaline. It has a high pH. That basic solution then grabs the acidic CO2 greedily, pulling it right out of the air or a flue gas stream.
And then to release it.
Then you literally flip a switch. You reverse the polarity. You use electricity to make the solution acidic with a low pH. As soon as it becomes acidic, it can't hold on to the CO2 anymore. The gas just bubbles right out as a pure stream.
And you can do this with specific molecules like quinones.
Yes, those are what we call redox active carriers. They are organic molecules that change their shape and their affinity for CO2 when they gain or lose an electron. It's like an electric magnet. Turn the power on, it grabs the carbon. Turn the power off or reverse the polarity, and it drops it.
And the huge benefit here is that you don't need a steam cycle. You don't need a giant boiler. You could, in theory, just plug this system into a solar farm or a wind turbine.
Exactly. It allows for much more modular systems. You could have smaller decentralized units right next to a factory, and it fundamentally decouples the process of carbon capture from the need for massive centralized heat generation. It electrifies the whole process.
Now, we mentioned mineralization earlier as the safest, most permanent trapping mechanism turning the gas to stone. But we also said nature takes centuries or millennia to do that. There is technology out there that's pushing to speed that up dramatically. We have to talk about CarbFix.
The CarbFix project in Iceland is, well, it's really captured the imagination of the scientific community. Their approach is completely different. They aren't trying to store CO2 as a supercritical gas. They are dissolving it in large amounts of water, basically making industrial-scale soda water and injecting that water deep into basaltic rock.
Basalt is volcanic rock, right, which Iceland has plenty of.
Iceland is pretty much made of basalt, and basalt is a highly reactive rock. It's chock full of the elements you need for mineralization: calcium, magnesium, and iron. So when that acidic CO2-laced water hits the fresh basalt, a chemical reaction happens very, very quickly.
What's the reaction?
The acidic water starts dissolving the rock, releasing those metal ions, and those ions then immediately combine with the dissolved CO2 to form solid carbonate minerals.
And how fast does this actually happen?
This is the amazing part. In traditional sedimentary basins, geologists thought mineralization might take centuries or millennia. In the CarbFix project, they found that over 95% of the injected CO2 had turned into solid carbonate minerals in less than 2 years.
2 years.
Yeah.
That is lightning fast in geological time.
It is basically instant. And think about what that means for safety and security. We talked about all the risks of gas leakage from faults or old wells, but you can't leak a rock. Once it mineralizes, it is the safest, most permanent form of carbon storage we currently have.
So why don't we just do that everywhere? What's the catch?
The limitation is geology and water. You need basalt, which is common in some parts of the world like Iceland or the Pacific Northwest, but not everywhere. And you need a lot of fresh water. The current process uses about 25 tons of water for every 1 ton of CO2 you want to store, so it's an incredible solution, but it's geographically limited.
We're also seeing new types of solvents emerging to replace the old amines, things like ionic liquids.
Right. Ionic liquids are really interesting. They are essentially salts that are liquid at or near room temperature, and their superpower is that they have almost zero vapor pressure.
Meaning they don't evaporate.
Exactly. So that pollution problem we talked about with the amines is the toxic fumes getting into the atmosphere and creating nitrosamines. Ionic liquids don't do that. They stay in the liquid phase. They're also much more chemically stable, so they don't degrade as quickly. They're still very expensive right now, but they could solve the toxicity and pollution issue, which would make permitting these plants much easier in the future.
It's amazing to see the chemistry catching up to the problem. It really feels like we are moving from the brute force era of just boiling massive amounts of water to a more elegant, smart design era of MOFs in electrochemistry.
That is the hope. That is absolutely the frontier. But, and there is always but technology doesn't exist in a vacuum. It exists in society. And this brings us to our final section for today, the implications, the ethics, the economics, and the justice of it all.
This is where the rubber really meets the road. We can have the best, most efficient MOFs in the world, but if the economics don't work, or if it hurts communities, it simply won't scale.
Exactly. You can have a perfect solution on paper that fails completely in the real world.
Let's start with environmental justice. We have a source here, a really important study from Wyoming by a team led by Middleton in 2025. What did they find?
What they did was pretty simple, but the results were powerful. They took a map of the proposed routes for new CO2 pipelines and the likely locations of future storage sites, and they overlaid that map with demographic data from the census income levels, racial demographics, and so on.
And what was the correlation they found?
It was disturbing, but perhaps not surprising. They found that the infrastructure, the pipelines, the injection wells, the compressor stations disproportionately overlaps with disadvantaged communities, low-income communities, and communities of color.
So the very same people who have historically borne the brunt of industrial pollution, the ones living next to the power plant or the refinery, are now being asked to host the waste pipelines and disposal sites for the solution.
That's the issue. The burden is intensely local. They get the risk of a pipeline leak, they get the disruption from construction, they get the land use issues from eminent domain. But the benefit is global mitigating climate change, or it's corporate, in the form of carbon credits and tax breaks. It creates a serious equity imbalance.
It raises the really tough question. Are we solving the climate crisis on the backs of the most vulnerable communities?
It does. And if we don't address that engagement and equity piece from the very beginning, these projects will get blocked by local opposition. We are already seeing huge public pushback against pipeline projects in the American Midwest for exactly these reasons.
Then there's the pure economic aspect. We talked about the valley of death for new technologies.
It's the classic problem. You have incredibly high capex, that's capital expenditure. It costs billions of dollars to build one of these capture plants. And then you have high opex, the operating expenditure, driven by that energy penalty we discussed.
And the sources mentioned that things, well, they break when you leave the lab. The real world is messy.
Right. It's one thing to make a novel membrane work perfectly with a clean, controlled stream of gas in a laboratory. It's a completely different challenge to make it work reliably for 20 years in a dirty, hot, corrosive smokestack.
So the performance in the real world drops.
Significantly. The research on membranes, for example, shows that lab performance often drops by 15 to 30% in real-world industrial settings. The membranes get fouled with ash, they get clogged with particulates, they get degraded by other chemicals. This increases costs and reduces efficiency. The industry has to bridge that massive gap between it works in a beaker and it works in a dirty coal plant for decades.
And beyond the cost today, we also have to touch on the intergenerational ethics of all this.
The stewardship problem. This is a big one. If we inject billions of tons of CO2 gas deep underground into these saline aquifers, someone has to watch it. Someone has to monitor it for pressure changes and leaks. But for how long?
Centuries, millennia.
At least centuries. We are essentially creating a long-term liability for our great-great-grandchildren. We are burying a potential problem and handing them the monitoring equipment and the responsibility. It's a very similar debate to the one we have around nuclear waste.
Is it ethical to leave a legacy of permanent maintenance to a future generation that didn't create the emissions in the first place?
That is the core question. We are making a bet that our geology is perfect or that future technology will be better at managing it if something goes wrong. But if a storage reservoir starts to leak in the year 2100, who pays for it? The company that injected it might be bankrupt or might not even exist anymore. It inevitably becomes a public liability.
And finally, that brings us to the moral hazard. This is the big philosophical one that hangs over the entire discussion.
It's the argument that keeps a lot of climate scientists up at night. The question is, if we believe that CCUS will be our technological savior, do we stop trying so hard to quit fossil fuels?
The idea that, oh, it's fine, we could just capture it later, so let's keep burning oil and gas today.
Exactly. It's the diet pill analogy. If you believe you have a magic pill that will instantly cancel out all the calories, you might just keep eating junk food instead of changing your diet. The promise of a future technological fix can create a powerful incentive for inaction today.
And the risk there is about resource allocation, isn't it?
It is. Every $1 billion spent building a massive CCS project is $1 billion that was not spent on deploying more wind, more solar, or more battery storage. There is a very real fear of overshoot scenarios in climate models. These are scenarios where we allow global temperatures to rise past safe limits because we assume we can use technologies like CCS and D to suck all that carbon back out of the atmosphere later in the century.
But if that technology doesn't scale as fast as the models hope,
if the MOFs don't work as cheaply as we want, or if we run out of safe storage space, then we're stuck. We're stuck in the heat. We've burned the carbon and discovered we have no reliable way to catch it after the fact.
So after this whole conversation, what does this all mean? We've covered so much, from the lone pair of electrons on a single nitrogen atom all the way up to the ethics of intergenerational liability.
I think the biggest takeaway is nuance. CCUS is not a silver bullet. It is not a magic vacuum cleaner that absolves us of the difficult work of transitioning our energy system. It is a complex, heavy industrial tool with very real chemical limitations, geological risks, and societal costs.
But with breakthroughs like the 2025 Nobel work on MOFs and the incredible advances in electrochemistry, it's a tool that is getting sharper and more efficient every year.
It is, and it's a tool we will probably need, especially for the hard-to-abate sectors, things like cement production, steel manufacturing, maybe long-haul aviation. We can't run a cement kiln on batteries easily yet, so we will likely need capture for those essential industries. But we have to use this tool with our eyes wide open to the costs, both economic and ethical. We can't just wish the physics and the geology away.
And that, I think, is the perfect place to leave it for today. A mix of cautious optimism and deep realism. We need the innovation, but we also need the wisdom to deploy it correctly and equitably.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stat Studios for more informative content and support us in Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.